Got it? All right, I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. I thank you for these students. Pray with this day, help us to just use this time wisely to review the material. And I pray that they would just do their best for your glory on this Wednesday, Lord. In your name I pray. Amen. Okay, so any questions?
Everything.
Yeah.
That's not a question.
Can we do everything?
No, we have like 45 minutes. So what's that? 29 and 33. Now, of course, I will post the solution to this, of course, as soon as I get a chance. So the argument, all you really need to do this problem is a clear understanding of the definitions. So first of all, to show two things are equal, what you can do is try to show that they have matching columns. That's the approach I took. I mean, there are other approaches, but this is the approach I took. So what I'm trying to do is compare the jth column of this to the jth column of that. To prove two column vectors are equal, I can show that their ith components match. So I just start with the ijth component of AB. Well, make some matrix multiplication says that that's sum k equals 1 to n of this, by definition of matrix multiplication. But hey, that's exactly the jth component. This is the jth column of B, the kth component of that, by definition of column. But hey, this is exactly the matrix column product of A times the jth column of B, ith component of all that. So if this is equal to that, for arbitrary I and j, that shows that A, B, I, j is equal. I mean, it shows that the jth column of this is equal to the jth column of that. Well, it's equal to that, rather. But that's exactly what you're trying to prove, is that the jth column of this is A times the jth column of B. So, yes, sir?
Are you putting the solution on Blackboard?
That is the plan, as soon as I get a chance after class. As long as I don't get distracted. I will try very hard not to get distracted and do it. If like 5 o'clock has rolled around and I haven't posted it yet, or not even 5 o'clock, if like, see what time is it? 12. So if like it's 2 o'clock and it hasn't been posted yet, you should email me. That means I forgot. Okay? I would not be offended. I get like 50 emails. Yeah, that'd be fun. Okay, so I mean, this is a question about notation, right? You're like, it's just about notation. Yes, that's true, but notation matters in here a lot. So, what's the next one?
Just a quick question on the nilpotent matrices. With the I, was that just the identity matrix, or was that a matrix with all zeros?
I should always be understood to be the identity matrix, unless something else is, Okay. I mean, I is almost always just the identity matrix. So here, I mean, problem 30, part of its charm is I don't tell you how big the matrices are, right? They could be, I mean, who knows what size they are, right? I mean, I don't think I can do it. I don't think I can get away with 2 by 2 matrices having these properties, but I think like starting at 3 by 3, I could get it. 4 by 4, 5 by 5, whatever. I don't think there's not enough richness in the 2 by 2 case to get it. But anyway, you don't need components to do this. You just need matrix algebra. So like I said, try this as a template. If you multiply this out, you get that. Of course, n cubed is 0. And so you collect terms. You've got like A plus B, and B plus C. So, what can make this work, of course, is A equals to 1. And I want this to be 0, and I want that to be 0. Then I'd have this equation working. So it suggests I make an educated guess that I plus n inverse is I minus n plus n squared. And then this is not a proof, right? The proof's down here. This times that is that, which is not. So there. And as we proved, if you have, if it's a right inverse, it's automatically a left inverse. We have paid our dues and proved that in here, so you can use that in problems like this if you want. Like I wouldn't also insist that you also show that I plus n multiplied on the other side also gives you that. If we get one side, we get the other. Yes, sir?
How did you come up with, like in the homework you put a hint saying to multiply by A, I plus B, n plus C, n squared, and then see where you go from there? How would we like arrive arrive at that, or like come to find out that that's going to be multiplied, or is that just some?
Well, in the notes, we saw that if I have I plus n, then I minus n serves as an inverse, right? Well, provided what? Degree 2. So once I see that works, it makes me think, maybe I can generalize that.
Okay.
That's where it came from for me.
Okay. So it's just something to help you find the inverse, like something you can set up yourself in a way.
Right. I mean, this is generally a thing in math, right? If you're asked to find something, you can make an educated guess about what you're looking for.
Okay.
It may or may not be a reasonable guess. If it's not a reasonable guess and you try to work it out, you'll get contradiction and you'll have to look elsewhere. But this kind of logic is especially popular in differential equations. Guess a general template for the solution, plug it in, see what happens. Yep.
Can we look at the one where you did elementary matrices?
Absolutely. Which one was that? There's a couple of them. 36, yeah, sure. So I have this matrix, 1, 1, 1, 3, 2, 0. And then I do row reduction, right? So I subtract thrice, that's not a word, thrice. Thrice the first row from the second. Obligatory, this is nothing to sneeze at. Let's see here. Then, so then minus row 2 gives me that, right? And then row 1 minus row 2 gives me that, at which point I'm done. That's the reduced row echelon form of that guy. Now your question was, how do I see the elementary matrices? Okay, so basically I do the same thing to the identity matrix. So like to get from this to that, I would just take the identity matrix and do like row 2 minus 3 times row 1, which is this, right? If I take minus 3 times this, from that I get minus 3, 1. Do you see that? And then, the way it works, let's try it out. Let me show you what's going on here. So 1, 0, minus 3, 1. And then let's look at like the matrix, which was what, 1, 1, 1. 3, 2, 0, right? And so what's that equal? One. Minus 3 plus 3 is 0. 1. Minus 3 plus 2 is what? Minus 1. And then this gives me 1 minus 3. Which, as you can see, is precisely what the first row reduction gets us, right? See that? So multiplication by this elementary matrix on the left is equivalent to that row reduction. We always have this pairing between elementary row operations and multiplication on the left by an elementary matrix of the same type. Right. So, yeah. These. So, well, I'll just stop there. Other questions? Yes, sir.
And so usually you're going to work out that you have the same amount of operations as the UE?
Yeah, there's one E for each operation. The number of operations is not unique. Like if you go a different path in the reduction, you could end up with 3 or 5 or different numbers. You could go in loops. You could find a way to make it take 300 row operations if you're sufficiently bored or really, really lost, and yet good at arithmetic. Okay. Usually at some point when we're lost, we make an arithmetic mistake, and then everything past that point is garbage. Unless you make an equal and opposite counteracting mistake and get back on the path, but those are harder to make. I digress. Next question. Yes, sir.
37.
37. Okay. Now 37 is kind of a novelty. Here I'm looking at column operations, which is not, 37 is kind of just an end to itself for now. I wouldn't expect that I would test on 37 per se. It's, you can do column operations like this. And if you do corresponding column operations on the identity matrix, if you multiply the matrix on the right by one of these guys, it does the same column operation. So, but we're mostly interested in row operations because we encode equations as rows, so this is just kind of a novelty, this problem. I would worry about all the other homework problems before this one in my studying. Other questions?
Can we expect the breakdown to be the quiz as far as like?
I would expect that I try to cover all of the material as deeply as possible, given the hour I have to test you.
Proofs versus calculus, right?
Doesn't matter.
Doesn't matter.
Just try to understand everything. Okay, fine. It's probably like 70-30.
Which way?
Oh. Yeah. See, I don't like to say this because then what's the proof problem in the eye of the beholder? I really want you to understand the different things we've said in here. So what some people might perceive as a proof problem, other people would say is a computational problem. So these kinds of I will say this: it's likely that I ask you at least one of the concatenation proposition kind of thing. I might ask you to prove, like we had this one in the homework. I've certainly put this on tests before, right? I put that on a bunch of tests. This one is certainly fair game, right? Other things like this, These sorts of proofs, these there has to be something like that on the test, at least one of these guys. I would expect that there's an inductive proof somewhere. So we've done that. There should probably be something about complex arithmetic and modular arithmetic somewhere because I've made a big deal of that. There will certainly be calculate the reduced row echelon form of a given real matrix. I mean, that is an inevitability. Will there be a spanning question? Yes. Will there be a linear independence question? Yes. Will there be a problem where I just give you the reduced row echelon form of a matrix and expect you to work with it without further calculation, just interpretation? Yes. Almost certainly that will happen. But I can't really answer the particular point breakdown at the moment. And I probably shouldn't either. Yep.
What exactly do you mean by on the interpretation and no more calculation? Like you use that terminology on the mission too, and I was a little confused.
Well, it was overly optimistic on my part in that problem. Well, here, let me show you an example of that. What I mean by that is something like this. Suppose you're given that the reduced row echelon form of V1, V2, T1, T2 equals to, I don't know, 1, 1, 1, 0, 0, 0, 1, 3, 0, 0, 0. Oh, that's too stupid. Make it 1. 1, 1, 0, 0, 1. So there I could say, what was it just? I know I've lost the words, Adam. What did you say?
You mentioned like you have to work with it by just interpretation and no calculation.
Right.
What does a problem like that look like?
Something like this, where I say, explain why V1 and V2 are linearly independent. Well, clearly, E1 and E2, which are columns what? 1 and 2 of, let me call this thing, I need to give this a name, I'm tired of writing it, A. Are linearly independent. Therefore, by CCP, there does not exist a linear dependence amongst columns of A, aka V1 and V2, right? Or another thing I could argue by interpretation without further calculation is that since, column, let me give a name to this. Let me call this R1, R2, R3, R4. I'm somewhat violating the spirit of what I was just telling you to save myself writing. But since R1 plus R2 is equal to R3, the CCP, the column correspondence property, some people call it the linear correspondence, implies that V1 plus V2 is equal to T1. There's another example. There's really no calculation to do. It's just by inspection and my knowledge of the... another example of this would be something like, suppose I know the reduced row echelon form of A concatenated with the I is equal to M concatenated with I, where M is some specific matrix which is given. Oh, I'm sorry, other way around. I am, right? And maybe M is actually a given matrix. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, whatever. I'll make this a 42 just for good measure. There we go. So was this without further calculation, I can tell you that A inverse is what? It's 1, 2, 3, 4, 5, 6, 7, 8, 42. Because of the theory we've worked out. So a typical place where I say something like that is a place where I want you to use the theorems that we've developed, not to go back and try to solve equations explicitly. Yeah. You had a question?
I just wanted to ask, also from that first one, would you be able to say that T2 would not be in the span of V1 and V2?
Indeed.
At 0.
Right.
Yeah.
Yeah.
That's not equal 1.
Exactly. Since the fourth column is clearly not a linear combination of the first three, right? There's no way you can get this 1 here from these zeros. It follows that, in fact, yes, T2 is not an element of the span of V1, V2, T1. Yeah, T1 is an element of the span, as is exhibited by this linear combination right there. T1 is in the span of V1, V2. For example. Yeah.
So if you were to take the first 3 columns together of that,
Ah.
I can say that that would be a linearly dependent span, but if you add in the 4th column, it becomes linearly independent because...
The first 3 columns are linearly dependent because of this linear dependence right here.
Right. But then if you take all 4 together, it's not linearly independent anymore.
It's not linearly independent to start with. These 3 columns are linearly dependent. There's linear dependence right there.
Right.
What are you saying?
Yeah, so the first 3 columns together are linearly dependent.
Yes.
Like if you made a span with the first 3 columns, you'd have linear...
Yeah, if you add more vectors to a linearly dependent set, it's still linearly dependent.
Right, okay. Got it.
The only way to take linearly dependent and make it independent is to remove things.
Okay.
Like in this case, to remove, you can either remove any 3 of these. If we remove any one of these 3, it'll be linearly independent as it happens. Other questions? Yes, sir.
Would we be able to go over the proof of the, I forgot the number, but the one with like a law of exponents, where it was like...
Yeah. Certainly. Let's see here. You guys are good on the symbolic row reduction problems? Good? Okay, good. See here, where was I? Which one was that? Was that... Here it is. This one, right? So this is more of a drag if we haven't already proved. See, in the notes we've already proved that this is that. So that's very, very helpful. But basically I just start by saying, okay, well, it's true for q equal to 0. It's true for q equal to 1. I just want to settle those cases because notationally they're a little bit different. And once that's settled, then I look at an arbitrary q, in here for some fixed p. I suppose inductively that a to the p, parentheses raised to the q power, is a to the pq. And then I consider a to the p to the q plus 1. I'm doing induction on q here. But by definition, this is a to the p times a to the p to the q, right? And then by induction hypothesis, this is a to the pq. Then I use part 1 of the proposition, which we proved in the notes, which is that. And then I just do algebra to see that that's p times q plus 1, which is the claim, the induction hypothesis for q plus 1. Therefore, by induction, a to the p to the q is a to the pq by induction q, but p was arbitrary, so we got it for all p and q, non-negative. It's actually a little bit easier than the one I had in the one I have in notes is kind of a little bit more annoying. It had more steps, as I recall. Other questions? Yep.
Sometimes, yes, that would be like, right, part 1 of proposition 2 before development. Is there a name?
Oh, you would just say, you probably should ask me, am I allowed to assume that?
Okay.
Hopefully if I had written this on the test, I would say something like, you're allowed to assume that, you know, you're given that a to the p times, let's say a to the r times a to the s is equal to a to the r plus s for non-negative integers. Like that if I wrote the problem properly, I would have included that in the problem statement. I do not expect you to memorize proposition numbers and stuff in here. There are a few things I want you to be able to call out by name. Like, I want you to know what the column correspondence property is, so you can say by CCP. You do not have to write out column correspondence property, right? There are many notations in here I expect you to know, like unflinchingly and carefully. Definition of matrix multiplication, definition of matrix column, row matrix, like all of the matrix multiplications that we talked about in here. You need to know those. You need to know how to prove, you know, 2 matrix expressions are equal by looking at components, right? Some of you are not comfortable with that yet. You should work on that. Let's see here. Let me go back up to the top. Do you guys understand this problem 27? We're asked, is this linearly independent for what value of k? So what you do is I try to look for non-trivial solutions to this equation, right? So I can do row reduction on this matrix. And when I do that, I have to let k ride along as a variable, right? And when I do that, I eventually get to this step. So in order to go further, I have to divide by k minus 5, which of course you can't do if k is equal to 5, right? So basically what we find then is that this is going to be the ultimate row reduction, which means it's just the homogeneous solution, just the trivial dependence. When k is not equal to 5, but k equals to 5, we have linear dependence. In fact, I can exhibit it explicitly like so. 1, 2, 3 plus 2, 2, 2 is 3, 4, 5. That's k equals to 5. Yep.
Could you just say by CCP that, like from the very beginning, basically, that you know that k cannot equal 5?
Yeah. Very good. Indeed, that kind of laziness I approve of. We would all like to be that lazy. Now, I didn't do that because, while those of you who wrote that in your solution would be delighted to see it in mine, those of you who didn't want to see this, right? Oh man, I wasn't as lazy as I could have been. Curses, I've been out-lazied. Ah, man, the student has become the master. Curses, what shall I do? Okay, sorry. Next, what else would you like to talk about? Yep.
33, which is the diagonal.
Ah, yes. I wonder how many of you got this one. So what I do is, here's an arbitrary matrix D. I'm given that AD is equal to DA for all A. So I pick my favorite A to work on, in particular the matrix unit, EKL. So on the one hand, I have EKL times D. On the other hand, I have D times EKL. These have to be equal, but I can multiply the expansion for D in terms of the matrix units, like so. This simplifies to Kronecker delta Li EKJ. This simplifies to Kronecker delta JK EIL. So I've got this is equal to that, which is pretty sweet, right here like this, because it does a weird thing. It relates rather different components of D in this way. And then what I do is I look at the a bth component of that to try to get an actual honest to goodness equation here. So I look at the a bth component of this. Now the a bth component of that, it's only non-zero when I is equal to a and L is equal to b. And on the other side, it's only equal to 0, not equal to 0 when a is equal to k and I is equal to b. All right, so that squashes the sum and leaves me with this wonderful equation, dLb Kronecker delta Ka is equal to dak Kronecker delta Lb. And then I just do case-wise analysis. For example, if L is not equal to b, that means this is 0, which means that this is 0, but this can be non-zero, so all I got to do is look at like k not equal to a, and bam, I've got dLb is equal to 0 for L and b not equal. In other words, all non-diagonal entries are straight up 0. And then I focus my attention on L equals to b. L equals to b. Well, if L is equal to b, that means that Kronecker delta Lb is 1. So I've got like dBb. I've got this is 1, right? So I've got dBb because L is equal to b. dBb Kronecker delta Ka is equal to dak. But if you put k equals to a, I mean this is true for all indices, so I can in particular put k equals to a. And when I do that, I get dBb is equal to daa for k equals to a. But since a and b are arbitrary, that means that all of the diagonals are equal. In other words, the matrix is simply a scalar multiple of the identity. This is within all of your grasp. You just have to embrace the index notation and work with it. I don't think this is an easy problem. Yep.
We also have done an approach where we kind of play with inverses and multiplying on both sides like inverses.
But we don't know that inverse exists because this lambda could be 0.
Okay. I mean, like, we can't just say assuming that like the inverse is
And a priori, before the fact, it could be that I've got a matrix like, 3, 3, 3, 0, 0, 2, 2 down the diagonal or something, which also would not be invertible. If you're also given that D is invertible, there's probably an easier proof, yeah. But it begs the question, how do you know that? The purpose of this problem is to showcase the index method. I think I've achieved that much, if I have confused all of you. Sorry about that. It is a rather nice result, though, right? It's just a multiple of the identity. The fact that the identity in there is not surprising. The fact that only multiples of the identity are in there, that is a little bit surprising, I suppose. Other questions? There must be other questions.
You just go over
I'm sorry?
You just go over 28.
28?
You kind of did it already, but
Ah. Oh yeah, I skirted past that. I didn't really do it. So basically the point here is, it's kind of like the one I was hypothetically talking about over there, right? That's why you said that. Cool. So the first three columns are like the S1, S2, S3 corresponding to that. The last two correspond to the T1 and T2, right? So any linear correspondence I can see in the reduced matrix is also going to be present in the original matrix by the column correspondence property. So in particular, I can see that the third column is just the sum of the first two, right? Like this plus that is that. So that means that S1 plus S2 is also S3. So clearly S is not linearly independent because there's a linear dependence, which is non-trivial.
the span of S is
What about the span of S? I don't know. I mean, I could say the span of S1 and S2 is equal to the span of S1, S2, and S3. Like S3 doesn't add anything new to the span, but I haven't thought much about these sorts of ideas in here yet. T is linearly independent because these are not, there's no way you can get one as a multiple of the other. By the way, here's a fun fact for you. You can use this if you want. Two vectors, linear independence of a set with two vectors, the fact that one is not a scalar multiple of the other is equivalent to saying that this has a no non-trivial solutions. See, because if you have, suppose you have C1 V1 plus C2 V2 equal to 0, right? For V1 V2 not equal to 0, and for C1 not equal to 0. Then what does that say? It says V1 is equal to minus C2 over C1 times V2, right? In other words, it's just K times V2. So the existence of a non-trivial, I mean, you can always solve for one of the vectors and get one as the other multiple of the other if you have linear dependence for 2. So it's easier to kind of eyeball one being a multiple of the other, right? In the case of 2 vectors, you can easily see whether one's a scalar multiple of the other. Seeing linear dependence or linear independence of more than 2 vectors is more complicated, right? Right. So, I mean, in terms of seeing linear independence, the one I'm sure about is, I mean, it's pretty obvious that if you have pivot columns, right, like if you have E1, E2, En, this is linearly independent, right? I mean, you can see that by inspection. Or if you don't believe me, you could prove it, right? This is linearly independent. There's no way you can build one of these from the other. There's simply no way to get the 1 in a particular one of those from the ones in the other because it's 0 in all those spots. That's like the mechanics of it. You could, of course, also, I mean, if you take a linear combination of these guys equal to 0, what do you get? What's this the same as? This is just notation for what? Right? But by definition of a vector, this is only going to be 0 of what? Right? So there you go. There's the proof that the standard basis is linearly independent. Just take a linear combination of them equal to 0 and show that the coefficients have to be 0. It's almost immediate. Yep.
So if you were to take just some other set that contained S1, S2, S3, and T1 and T2, and looked at the whole set, would that whole set be linearly independent?
Oh, I'm sorry I asked you guys. I just found the sheet up here. Duh. You were saying something before I got distracted. Bye-bye. I'm sorry. Say it again. Sorry.
If you took a set, just call it like A or something,
Uh-huh.
and it contained S1, S2, S3, T1, and T2, so in reference to the entire set. would
Now
you
the
say
union?
that-
You're talking about the union of these?
Yeah, the union of the sets. And then you looked at that as one set.
Mm-hmm.
Would you say that that's linearly independent?
No, that would be linearly dependent.
So
for sure.
Does it contain a part that is dependent? Like
Right. There's a linear dependence there. It's S1 plus S2 equals S3. Right. For example, there's others.
Yeah. So it doesn't have to be a combination of every vector. It's just-
No. It just has to exist a non-trivial linear dependence.
Okay, so as long as there is a dependence within the set.
Right.
somewhere.
Here's a stupid example. Here's a truly stupid example. If 0 is in the set, it doesn't matter what else is there. It's linearly dependent because 0 admits this rather annoying 0 vector times 1 is equal to 0. That's a non-trivial linear dependence that includes the 0 vector. That alone spoils linear independence. So, shall we go back to the first homework? Do you guys have any questions about the first homework? Did you guys come to terms with the induction we had to do there? So what's a ring? What's that? Something you put on your finger? Yes. Yeah. Okay. There's an addition and there's a multiplication. The addition is commutative. There's a 0, right? The multiplication is also commutative. For us, we talk about commutative rings. But with a ring, not everything has to have a multiplicative inverse, right? For example, I talked about Z mod 6Z, right? It's my kind of standard go-to example. So this is the first class that was that the Trump Day that I talked about? Trump Day. Yeah, Trump Day, I think I still said things, right? I did. Yes, I did. So in this, 3 bar times 2 bar. Of course, it's 0 bar. So 3 and 2 are 0 divisors, right? Which means that this is not a field. A field is a ring where every non-zero thing has a multiplicative inverse, right? So I do want you to understand those words I'm using. I probably won't ask you what the axioms of a ring are, but I'd like you to be able to calculate with them. And I'd like you to be able to have a clear understanding of what the difference is between a field and a ring, all right? Every field is a ring. Not every ring is a field, right? This is a ring, but not a field. Yep. Exactly. That's the key thing. In a field, we can divide by non-zero things. But in a ring, maybe, maybe not. Depends. In here, I can divide by certain things, right? Because like 5 times 5 is what? 25, which is 1. So apparently 1 over 5 bar is equal to 5 bar. So I can divide by 5, just not everything else. Okay. This multisets was really just an invitation to you to read my notes. I haven't really done much else with that. I wouldn't worry about that too much. I don't know if I can really ask an intelligent question about multisets anyway. It's just, it's there. I do expect you to be able to do these kinds of calculations, so I hope you can do those. I don't really have much to say about that. So I hope I've assigned you enough of these that you're at least starting to get comfortable with these kinds of things. I'll probably ask at least one row reduction that's over one of those guys. Obviously with a field. Maybe I'll ask you to do something like, here, I'll just do one for fun. What if we were going to do row reduction of 1 bar, 3 bar, 0 bar, 1 bar, 2 bar, 2 bar. And let's do it over Z mod, what do you guys want? 5Z? Okay, sure. Okay, so first of all, this is row 2 minus 3 row 1. That gives me 0, 2 bar, what, minus 1 bar? And then my next move, hey, cool, only need 2 moves. So yeah, the forward and backwards pass are now almost done. All I have to do is do what? It's almost in reduced or echelon form. What am I missing? Divide by 2, which is the same as what here? Yeah, multiply by 3 bar. So 3 bar times row 2. Now, the logic there is that 2 bar times 3 bar is 6 bar, which is 1 bar. So 2 and 3 are multiplicative inverses here. So 3 row 2 bar gives me 1 bar, 0 bar, 1 bar, 0 bar, 1 bar. And let's see here, minus 3 bar. Now I can clean this up a little bit. I mean, that'd be fine. If this was the question on the test, I'd be cool with that. But if I had added the extra thing, please leave your answer in terms of 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, as I might do. You know, leave your answer in terms of this as to make sure that I don't go crazy grading. Let's see here. Minus 3 is what? Yeah. By the way, that's one of the sort of more useful things you could do with those silly tables I was making you look at. I mean, just kind of fun thought. You can, from this table here, you can see like minus 2 is 4, you know. This shows me minus 4 is 4, minus 4 is 6, although this is not in a field, but I mean, that kind of comment applies to rings just the same. I will only ask you to do row reduction over a field. So I only would ask you over like Z mod 2, Z mod 3, Z5, Z7, Z11, Z13. Z17, Z19. But, I mean, come on, this something like 5 or 7 probably suffices. I really don't want it to get too large a number. Any questions about this? It's pretty much the same song and dance, right? Just that we have a little quirk of multiplicative inverses are a little funny. All right. This problem actually was innocent enough, but anyway. Here's typical induction problem. So any questions about this, or? Yeah.
So if you put in the inductive loop, you put in the 2k minus 1.
Uh-huh.
Are you supposed to solve that algebraically with that, or just keep it?
Well, let's see. So I start by assuming this is true, right? Then I want to show that this is also then going to be true when I replace k with k plus 1. So I got to start on either this side or that side and try to get to the other side. In principle, I could start with k plus 1 squared and try to get back over to here. But I just, for whatever reason, I think it's more natural to start with the left-hand side and plug in k plus 1 in there, and then just algebra. So like algebra, these first terms, right, by induction hypothesis, are exactly k squared. And then you're left with this one extra term. You FOIL it out and group stuff, and you get k plus 1 squared. And so I've showed that the same sum with k replaced with k plus 1 is equal to k plus 1 squared, which shows us that by the induction hypothesis true for k implies the induction hypothesis is also true for k plus 1. Therefore, by proof by mathematical induction, it follows it's true for all k, because we already showed the base step up here. It's true for 1, since 1 is equal to 1 squared. It's kind of, the base step is kind of unexciting, but there it is. I think the other one was harder, right? You do need to know the definition of finite sum. I didn't mention that yet today, but that's just because I forgot, It's not really that hard to prove things about finite sums if you just know the recursive definition, right? Like this problem was not that hard, right? As long as you know what the definitions are, right? I think I have said that enough. You need to know the definitions. Definitions are your lifeline. This one was a little bit tricky. So what I did was I assumed it's true, and I assumed it was true for n minus 1. And the reason I did that is because I have formulas for n minus 1. So I assumed n minus 1 was true and tried to show n was true. I thought that was more convenient in this problem. And so, there's alpha to the n, which is that times that. By the induction hypothesis, this can be written as that. That's not actually in the problem. I added that, this formula. But that's a standard Calc 2 thing. And although we have infinity here in Calc 2, it's the binomial series. And anyway, I distribute and split off the top thing and the bottom thing on either side and massage a little bit. Use the definition of the choose symbols there. And out pops the formula for n. So n minus 1 implies n, therefore by induction on n, we get the binomial theorem. Seems unlikely as a test question for some reason. I don't know. I guess I could just ask you this one. There'd be time for this one. I am fond of this question, right? It's important, but here's where in the homework I asked you one that was kind of like things I had written over here but erased. How do you prove something like the scalar multiple of a plus b is equal to that plus that? You look at the ijth component, right? These parentheses, are they optional? No, those are part of the solution, right? Those are not like me just my joy of writing extra parentheses. I mean, I do, that is true. I do have that vice, but this is aij plus bij. This is definition of matrix multiplication, right? A matrix addition, rather. So these definitions, you got to know your definitions, otherwise you don't know how to do these. But I'm totally cool with a similar format to the one I've shown you. You can stack equations, put the comment to the side like that. That'd be fine. Yep.
Is the comment inside required?
Yes. Yeah.
Okay, so we need no definitions. What about theorems and propositions? We need specific theorems and propositions.
You should, of course, know the theorems and proposition we've gone over, especially how to apply them conceptually. In terms of proofs of those, I ruled out a few, which implicitly means I haven't ruled out the others. Which ones did I rule out? Generally speaking, if I've spent a long time in class proving something, I might expect you to be able to do it. Especially if I don't think it was that complicated. Let's see here. So, I mean, certainly any of these matrix, like any of the proofs in section 2.2 or 2.3 are pretty benign. I think you could do these. I mean, 2.3.14 was homework. That makes it especially likely. 2.3.15 we did in class. See here, so what I'm trying to get to, let's see here. I mean, I would not ask you, it's unlikely I ask 2.4.20 because I didn't do those in class. I just asked you to read them. And they're really more complicated versions of things I can test more simply with other things. I mean, it's an index calculation, really. And there are other index calculations I could test more simply and ascertain whether or not you understood things easily without that complication. The things I was really trying to get to here was, what did I rule out? I ruled out specifically the, what was it I ruled out? I specifically ruled out this one, proof of 2.6.16 and 2.6.18 and 2.6.19. I ruled out the proofs of those. However, I would like you to be able to know them, what they say. What do they say? For example, let me show you some applications of these. If I have V1, V2, V3, right, and these are a subset of R2, or just a ring with two things, I'm almost done, guys, then is this linearly dependent or linearly independent? Or can't I tell? Here's another question. True, false, possible. True, false, possible. Explain why possible.
Well, the first one
Has to be linearly dependent, right? That's one of these theorems. One of the theorems says that if you have, if I have a set of k vectors and k is greater than n, then they're linearly dependent. So that's what I mean. I want you to know that. Not a hard thing to know. Read the theorems, try to understand them. On the other hand, this is possible, but it doesn't have to be true because you could have a linear dependence between V2 and V3. It may not get everything. But I wouldn't expect you to prove those two. I might ask you one of the implications of the inverse theorem, remember? We had like that list of equivalent statements and we looked at how to get from one to the other. So I might ask you one of those. So. She was really sorry. She's okay. They're here really early for that class. I wonder what's going on with that. That's funny. Anyway, that's all I got for you guys. Uh-oh. Mr. Pedester is trying to get people to subscribe, most likely.